I'm Dina Bacovsky. I'm chair of the ETIP Bioenergy Working Group 2 on Conversion Technologies, and I will moderate today's webinar. This is a webinar of the European Technology and Innovation Platform on Bioenergy, and this is an industry-led stakeholder platform that brings together the actors from academia, industry, and civil society who are engaged in the development of sustainable bioenergy and competitive biofuel technologies. And one major task of ETIP Bioenergy is to address the technical and economic barriers to development and deployment of bioenergy technologies. We take the topical discussions within the various working groups of the platform. And so the Working Group 2 on Conversion Technologies is exchanging information on research, development and deployment on conversion technologies for the production of advanced biofuels and bioenergy in Europe. We are organizing a series of webinars with the purpose of providing information from industry and academia to you and to allow you, the audience, to pose questions to these experts. We are holding this series of webinars in cooperation with others, for example, the EU project MUSIC. The concept is that we invite one expert from academia who covers the basics of the technology and one person from the industry who updates you on the progress that they are making on implementing this technology. Within our cooperation with others, we aim at providing a twin webinar about 2 weeks after our ETIP Bioenergy Working Group 2 webinar. And the twin webinar then covers the same technology, but focuses more on how the technology could be further and more widely implemented. So the webinar today will be followed by another webinar on pyrolysis on the 8th of June, and that one will look into upgrading of pyrolysis oils to advanced biofuels for transport, but really focusing on the upgrading of these oils. The twin webinar will be organized by the EU project MUSIC, and we will forward their announcement to you. Our webinar today focuses on pyrolysis oil, and I'm pleased to introduce to you two highly acknowledged experts in the field, Tony Bridgwater, who is professor at Aston University, and Gerhard Muggen, who is managing director at BTG BTL. Each of them will provide some 20 minutes of presentation, followed by another 20 minutes of question and answers with you. We will record the presentations, but not the Q&A sessions. You can post your questions to the speakers in the chat, please, and you can already do so during the presentation. The speakers will then reply to your questions after the presentations. And I would suggest everyone keep their microphones muted to prevent unnecessary noise. So with this, I would like to hand over to our first speaker. Tony Bridgwater is a professor of chemical engineering at Aston University in Birmingham. He's specializing in thermal conversion of biomass for production of fuels and chemicals. Tony will provide a presentation on the basics of pyrolysis technologies, such as how the process works, properties of the product, and limitations of the process. So Tony, when you're ready, the floor is yours.
Thank you. I assume I press the show my screen.
Yes, perfect.
Is that okay?
Yes, works perfect. Thank you.
Good. Well, good afternoon, everybody. It's nice to be able to talk to you on such a beautiful day. Well, it's a beautiful day in Britain anyway. Sun shining and the garden is beckoning to go and be attended to. I'd like to talk to you about the pyrolysis of biomass in various forms. So I'll start off by explaining what pyrolysis is. So when biomass is heated in the absence of air or oxygen, then the biomass decomposes or devolatilizes into three products. And no matter what kind of pyrolysis, there are always three products: a solid char, a liquid, which might be bio-oil from fast pyrolysis, or tar and pyroligneous acid from slow pyrolysis, and a gas. And the product yields depend on the type of biomass, the vapor and solids residence time, and the temperature. There are several modes of pyrolysis. Fast pyrolysis, which is what most people are currently interested in, which is typically operates around 500 degrees centigrade with very short hot vapor residence times, typically less than 2 seconds, and a short solid residence times. And under these circumstances, you get up to 75% weight liquid and some solid and char and some gas. Then there's slow pyrolysis, which is a very old technology going back thousands of years. This is rather lower temperature, but much longer hot vapor residence times and very long solid residence times. And then you get roughly a third liquid, third solid, and a third gas. Torrefaction is a relatively new technology, and this is essentially low temperature pyrolysis, typically at 250 to 300, long hot vapor residence time and long solids residence time. I'll talk little about that later on, but the main product is a solid, typically 85%, and it's basically intensively dried and slightly decomposed biomass. Then there's gasification, when the main product is gas, it's up to 99% gas, with a little tar, which needs to be separated before most applications, and some solid, although all the solid that's produced is burned within the process. But this is high temperature, short hot vapor residence time, and a short solid residence time. And the upper temperature is limited by the need to avoid slagging or sintering of the ash in the biomass. So fast pyrolysis products, the objective of fast pyrolysis is to maximize the liquids. We have very high heating rates, and because biomass has low thermal conductivity, we need small particles of size of typically less than 3 millimeters. Also, some can use up to 5 millimeters in size, and less than 10% water, because all of the water in the feedstock ends up in the liquid product, and too much water has an adverse effect on the properties of the liquid. It can cause phase separation, it reduces the heating value, and it also has the advantage of reducing viscosity. So the general rule is to limit the water content of the feed to less than 10%. Clean wood gives the highest liquid yield of up to 75% weight on a dry biomass feed, and this is homogeneous, i.e. single phase and low viscosity. The charcoal forms about 10 to 15% weight of the products, and this contains all the alkaline metals that have a deleterious effect on the quality of the liquid. Now, bioil has been defined by ASTM as a liquid from biomass fast pyrolysis, and it specifies the conditions under which it's made. And bioil is now limited by this definition to the liquid product from fast pyrolysis of biomass. The liquid is homogeneous, and some of the key parameters are shown here. So I'm just closing the menu bar because it's hiding the slide. The water content is typically 25% weight. The pH, it's acidic, typically around 2.5. The specific gravity is high at 1.2. The elemental analysis, carbon, hydrogen, and oxygen. And the important thing here, the oxygen is typically around 37%, or between 35 and 40. And this is what gives the liquid some of the unusual properties and creates some of the problems in upgrading it into hydrocarbons. The heating value as made is around 17 megajoules a kilo, and you cannot distill it. I think the most anybody has achieved is around 50% distillation, even if you go up to very high temperatures and go under vacuum. This is one of the key differences between this oil and the oil that we're much more familiar with, made from crude oil. In terms of yields, this is a slide showing the 4 main products. The red line is the organics, and you can see that this peaks typically around 500. Lower temperatures, you're getting incomplete pyrolysis and lower organics yield. And as temperature goes up, the organics, which form the main part of the liquid, begin to reduce. The gas yield goes up as the temperature goes up. The char yield goes down as the temperature goes down. And the reaction water, which is not the water in the biomass, but the product of the pyrolysis reactions, peaks at typically around 550. And the important thing to remember is that the bio-oil that is discussed and reported on and worked on is the organics plus the reaction water plus the feed water. Now, the fast pyrolysis requirements, again, it's important to remember that it's the organics that provide the energy and the value in the product. These can be converted into chemicals or fuels. And the organics yield is therefore very important. Some of the basic requirements of a fast pyrolysis process are high heating rates. You need small particle sizes as biomass has low thermal conductivity. You need dry biomass, less than 10% water, because all the feed moisture ends up in the bio-oil product as well as the reaction water. A carefully controlled temperature I've just shown on the previous slide, 500 degrees C or around that, is optimum for maximizing liquid yield. You need rapid and effective char separation because the alkaline metals in the char are catalytic and reduce the liquid yield and quality. And again, you need short hot vapor resonance time, typically 1 to 2 seconds or less, because thermal cracking also reduces liquid yield. These don't sound onerous and they're not difficult to achieve, but understanding what those requirements are does help to understand how the processes work and what you can and can't convert. The fundamentals, I'm not going to spend long on this because many people have spent a great deal of time looking at the mechanisms for the decomposition of biomass. Broido and Shahrazado developed one of the early models for cellulose. This is only cellulose. And this is a typical pathway that's often followed by those modeling the process. So the cellulose becomes an active cellulose, and then this breaks down into the water, char, and gas, and a vapor and a liquid, which breaks down into a secondary tar or char and gases. Desmond Radlin from Canada spent some time trying to describe what the pathways in going from biomass to bioliquids are concerned with. And you can see it's very complicated. I'm not going to go through it all, but those who want to can spend a lot of time. But the top part is what happens in ablative pyrolysis. And then the middle grey circle shows the complication and the effect of acids and alkalines and transition metals on the processes of decomposition. This is just to show that it has been studied, but it's extremely complicated. Thermally, a particle of wood, excuse me, a particle of wood is heated on the outside and forms a layer of char, and the heat goes in towards the middle. So as a particle is pyrolyzing, there's an outside layer of char, partially pyrolyzed wood, dried wood, and unpyrolyzed wood in the center. And that shows how the process of pyrolysis goes into the center of a particle. Since I've already explained that the char and the ash is catalytically active, the products from the center of the biomass have to pass outwards through the partially pyrolyzed wood and the char layer. And that is one of the problems that gives rise to the effects of the catalytic effect of char and ash on the products. again, many people have modeled this process in looking at how you can describe and control the rate of pyrolysis and the products of pyrolysis. The fast pyrolysis process is made up of 5 or more basic stages. Firstly, the material has to be dried to less than 10%. This is because both the feed water and the reaction water report to the bio-oil. Comminution is necessary to maintain or control the rate of heating of the particle, and for fluidized beds, this is typically 2 to 3 millimeters. Circulating fluidized beds can be larger in size, and ablative reactors, of which I don't think there are any current R&D activities, can use larger pieces. And years ago, when ablative pyrolysis was used to make liquid smoke, then whole tree logs were sometimes used. So ablative pyrolysis is a process whereby the material is pressed firmly against a heated surface, and the area in contact ablates into liquid, which vaporize, gas, and solid. Then the fast pyrolysis stage itself, you need high heating rate, controlled temperature, short residence time, and rapid cooling of the products to avoid secondary reactions. Char separation is important to minimize secondary reactions and to keep the liquid as clean as possible. And finally, the liquid has to be recovered through a process of condensation, cooling, and coalescence of the aerosols formed in the process. So those are the essential stages in a fast pyrolysis process. Looking at it as in more of process terms, drying, grinding, pyrolysis, which in here is shown as a simple fluidized bed, more illustrative reasons. Char is removed in 1 or more cyclones. There's a quench, which is what we use ourselves, but there are other ways of cooling. But again, the important thing is to carry out the quenching as quickly as possible, followed by electrostatic precipitation to remove the aerosols. And the products from the quench and the ESP form the product bio-oil. The char is normally used to provide the heat for pyrolysis. It's recycled internally. I'll show you that later. And the gas can either be exported or used in the process or recycled to provide the fluidization gas. Many fast pyrolysis reactors have been developed. Some have been commercialized, and you'll hear about one of those shortly after I finish talking. Circulating fluid beds, spouted fluid beds, and transported beds have been commercialized very successfully. But the research community has tried all sorts of things like ablative pyrolysis, vortex, and you can read the list there. And what's interesting is the imagination that people have used to try to achieve the basic requirements in different configurations of equipment. Now, the more commercially orientated reactors are known as circulating fluidized beds or transported bed reactors, with the pyrolyzer shown on the left. The sand and the char are separated in cyclones and then returned to a secondary combustor where the char is burnt to reheat the sand, and the hot sand is then recirculated. This shows why commercially that there isn't a char product, because it's all burnt within the process. There's probably rather more char needed, but separating it out is not technically or economically feasible. So it's usual to burn all the char and the spare gas, the flue gas. The heat in that can be used, for example, to raise steam or provide local heat. And then downstream from that, it's relatively similar to the earlier process. The significant difference here is the internal recirculation and combustion of the product char. Many routes are available to go from biomass to biofuels, and biofuels are currently one of the important and hot topics of the research community. So in fast pyrolysis, you can gasify the liquid and take the syngas and convert it by a whole range of processes, which only a few are mentioned there, to either form alcohols, which can be further processed, or go directly into hydrocarbons. That is well known, and the advantage of the fast pyrolysis via gasification route is that the liquid contains virtually no alkali metals, and therefore there's no problem in the ash sintering or slagging in the gasifier. It's a very clean process, and gasification of liquids is easier technically than of solids. There's the disadvantage of the cost and inefficiency of the fast pyrolysis, but the advantages of using a liquid as a feed to gasification more or less balances out the disadvantages. However, most work has gone into looking at the upgrading of the vapors and liquids from fast pyrolysis. So reading across from zeolite cracking, there's a great deal of work currently being undergone into looking at how to use zeolites in cracking the pyrolysis products and forming particularly aromatics. There's a process that Keogh developed, which closed down some 10 years ago now, which had difficulties commercially. And ELITech are currently looking at zeolite cracking. There are some challenges to be faced to do with the deposition of char on the surface of the zeolite from the cracking process, and this means that the catalyst, the zeolites, have to be passed through a very quick stage of burning off the carbon, and this is very similar to an FCC unit in a refinery. The zeolite cracking operates on the vapors from fast pyrolysis. Hydrotreating is based on the deoxygenation of the liquid, and this is a process that has been studied for 40 or 50 years, and surprisingly little advance has been made because of first partly the hydrolysis of catalysts and partly the kinetics of the various processes. And hydrotreating works seem to have significantly reduced in recent years. But it is a way of adding hydrogen to remove the oxygen of water, which then phase separates. The liquid bio-oil can also be blended with a variety of other liquids like biodiesel, and you can form esters as well. And the opportunity to recover valuable components and fractions from the liquid bio-oil is quite valuable and quite important. Catalysts are really important, both the catalyst you want and the catalyst you don't want. There are natural catalysts in the biomass, particularly potassium, which is particularly active in cracking organics to CO2 and water, and therefore this reduces the liquid yield. The potassium of all the alkaline metals is the most active, and is accumulated in the biomass partly as a necessary a growth agent in the biomass, and some control of it is important to avoid loss of yield. There are also heavy metals such as iron from the soil, from growing trees, for example, recovery of trees and dragging them through forests. Then the trees or the branches can accumulate soil and waste on the outside. There's also non-metals like sulfur, chlorine, and phosphorus, which may also be present. And lastly, the char product, which contains the biomass ash, and it contains a very large proportion of the biomass ash, especially the potassium. And this is why we want to remove the char as quickly as possible. Then we can add synthetic catalysts and we can put them within the pyrolysis reactor, which is not as effective as putting them ex situ close coupled, or in the case of hydrodeoxygenation of bio-oil, we can operate the deoxygenation using hydrogen remotely from the site. So we can transport the biofuel, the bioliquid rather, from the manufacturing site to a separate and remote facility for removing the oxygen. Not surprisingly, there's considerable interest in upgrading bio-oil to hydrocarbons to supplement or to replace the conventional fossil fuel derived materials. And it's the large proportion of oxygen that has to be rejected where most of the challenge is. The two main processes, one is hydrotreatment or hydrodeoxygenation, which rejects the oxygen in the organic compounds as water. And this is a high pressure process requiring gaseous hydrogen, typically operating around 200 bars. It's a complex process because it needs hydrogen, it needs high pressure, and you need to recover the unused hydrogen from the reaction. And recovery of hydrogen and recirculation at high pressure is challenging technically and economically. And so the studies that have been done have suggested a yield of around 15% of a naphtha-like product to be refined to diesel or to be fed into a conventional refinery. This was studied extensively in the 1980s and 1990s and through what are called the noughties. And although it's been extensive research, there doesn't seem to be much work ongoing now. Zeolite cracking does not require hydrogen, does not require pressure, and you effectively reject the oxygen from the process as carbon dioxide. This means, therefore, you're losing carbon, and it leads to less fixation of the carbon from the biomass, but it still gives projected yields of around 18% to be refined to gasoline or for use as aromatic chemicals. And in that point of view, it's important to remember that the aromatic chemical sector is the second biggest chemical industry in the world. So hydrodeoxygenation, zeolite cracking are variations of upgrading. And what's important is that there's a large number of catalysts and processes being researched and developed. And what's important, if you want to go down that road, is to understand what it is you want to make and define the quality of what you want. But for example, if you produce an upgraded product from bio-oil, you can either produce a final product by building into the process all the necessary upgrading, or you can send the partially upgraded product to a refinery to take advantage of all the upgrading processes and facilities and experience you've got there. But what's important in any upgrading is to clearly define what it is you want to make and what the quality is you want, because that will help to understand how much you can do and how much other people can do and where. And an interesting variation on that is that instead of trying to make something equivalent to a fossil fuel, there's the possibility of modifying the application to match the upgraded bio-oil characteristics. Then the second main area is pyrolytic gasification, which was on the initial table, which is a high temperature process to maximize the gas yield. An outline diagram is shown at the bottom of that, which was produced by Hermann Hoffbauer and was the basis of the Goosing plant and the other plants built in Austria that unfortunately have now stopped. And this is based on the right hand side gasification at up to 850 centigrade, which produces a medium heating value gas and a char. The char is then sent back to be combusted within the overall process, much the same as the circulating fluidized bed system I showed earlier. It's just so the whole system operates at a much higher temperature. The cost is higher and the carbon efficiency is lower because you're burning some of it all, but the gas quality is much higher. And in the case of the Goosing gasifiers, they fed the gas to some gas engines. So that's pyrolytic gasification. It was studied extensively in the USA. Richard Bailey was one of the advocates of this way back, for those who may remember. Then we have slow pyrolysis or carbonization. And charcoal's been manufactured for thousands of years, back to the ancient Egyptians, and it's still widely used for cooking, for example, in Africa, and it's also used for smelting metals. Brazil, for example, produces vast amounts of charcoal for smelting iron. And in Australia, they produce charcoal for smelting silica down to silicon. And there's also a well-defined market for charcoal application, particularly activated charcoal. This needs moderate temperatures with long residence times. In less developed areas of the world, small batch kilns are used. In more industrialized areas, multiple continuous retorts are used. A key feature of slow pyrolysis is the co-production of liquids, both organic and aqueous, which phase separate, and if you can't find a use for them, they require disposal. And one way, of course, is to burn the liquids to produce the heat in the pyrolysis. These are pictures of the usine Lambiot plant in France, which closed down in 2002. There were two retorts you can see there, and a very sophisticated chemicals recovery unit. And on the right-hand side, you can see the primary distillation column. Behind that, there was a multiplicity of separation and purification techniques for recovering some fine chemicals. This is a summary of the mass balances and finances of that operation at the turn of the century. So the facility processed around 95,000 tons per year of wet wood. It made around 25,000 tons a year of charcoal. It made some pyroligneous liquid, which includes water and organics. And the charcoal was valued at, I've conservatively estimated around €100 a ton, which gave a charcoal value of roughly 2,500 or 31% of the total income from the plant. There were acids and alcohols recovered, some oils and some fine chemicals. The notable thing here is that of the 95,000 tons a year of wet wood, 56 tons of fine chemicals produced the most income from the process. Some of the organics were also used as fuel within the process and within the refining. But the important thing I want you to note is that the total organics contributed over 2/3 of the income from the plant, and a very small amount of fine chemicals contributed over 1/3. And this is the opportunity, I think, in the biomass and biomass pyrolysis area, the opportunity to seek, find, and exploit the fine chemicals. And you can see here that given the right understanding of the chemistry and the processing and the market opportunities, then the opportunity for significantly enhancing the economics is significant. Biochar is talked about a lot. It's charcoal made by slow pyrolysis, and it's used as a soil amendment for soil health benefits, and it also provides long-term carbon sequestration. Biochar is a stable solid, and residues have been found in South America going back thousands of years. And it's the microstructure of the charcoal which provides the features, which is mainly water retention and microbial hosting, which encourages activity beneath the surface of the soil. There's a great deal of work has gone into attributing char characteristics to crop improvements, especially crop yield. And there are some quite extravagant claims made. So biochar is one of the currently popular products from pyrolysis and offers significant advantages. Torrefaction, I mentioned earlier, this is essentially low temperature pyrolysis, and the purpose of this is to enhance the biomass by removing water, reducing the hemicellulose, thereby improving the heating value, and particularly it was originally developed to improve the friability of the product for grinding and co-processing, like adding biomass into coal-fired power stations. There's a small amount of the vapors that are produced, roughly 15%. These can either be burnt to provide some process heat, or burnt to dispose of the waste, or collected to yield potentially valuable chemicals. Using tonified biomass as a form of biochar has been proposed, but it's not well understood, and there's no long-term experience of how long it lasts in soil. Many companies started up in Europe to develop torrefied biomass, but the economics were not sufficiently attractive, and many of them have now been closed down. So the promise of fast pyrolysis: you get a valuable, useful liquid, you get a valuable charcoal byproduct where you can recover it, high yields, high efficiency, no external energy, minimal emissions, and the product is valuable as an energy carrier for heat, power, chemicals and commodities, and transport fuels. Thank you very much, and I'm sorry if I've overrun slightly.
Thank you very much, Tony. I think that was a very interesting presentation on the fundamentals of pyrolysis and all the different forms it can take and the different products. No problem with running a little over the 20 minutes, but I encourage everyone to post questions in the chat. So far, I cannot see any. I don't know whether T sees questions in the chat yet.
Not in the chat, but Dina, you have another line with questions, 2 or 3 rows above. Maybe you can also see that.
Oh, no.
Okay. So maybe just
but probably you go ahead, and we have around 12 minutes time for questions to Tony, Q&A.
Yeah, so one question from the participants was, what is the correlation between solids and biomass fixed carbon and biomass feed particle size?
I only heard the first part of that, I'm sorry.
Okay. The question was about what is the correlation between solids and biomass fixed carbon and biomass feed particle size?
I don't think there is a relationship. The particles in the bio oil come mainly from lack of capturing the charcoal particles from fast pyrolysis. It's a question really on the design of the system as to how many particles escape the cyclones or filters or whatever system is in place. A little work has gone in trying to relate the amount of solids, but the proportion of carbon particles in bio oil, if that's the question, is typically less than 0.01%. It does depend on the design and the design of the process and the regularity of the process in operating smoothly to avoid any peaks and troughs or surges in the gas flow rates through the system.
Okay, thank you. Another question was how to remove char quickly from the continuous pyrolysis process.
The usual method for speed and reliability is to use cyclones, an initial what's often called a coarse cyclone followed by a fine cyclone. You need to remove as much char as quickly as possible, but then that was found not to be very successful, and therefore most people added a second cyclone. So you usually got two in series. I guess Gerhard will be able to comment on what he uses. Cyclones do depend on a regular and constant flow of gases. Any changes in the flow rates will lead to overloading or underloading in the cyclones and lead to carryover of char.
Thank you. Is there any process to separate water from produced bio-oil?
It's possible to use special kinds of evaporation, vacuum distillation of the water, but they're often deployed in laboratories, and while they are successful, the application on a large scale is expensive and not entirely satisfactory. Most people have used the bio-oil at around 25% water as is. If there's, and I think the difficulty with water is that water has a number of aspects on bio-oil. Water reduces viscosity as the water content goes up. It reduces heating value, and it reduces stability. So water, it has a complex effect on various properties of bio-oil. And if you, for example, reduce the water content of the feedstock, you can lower the water content of the bio-oil, but the viscosity becomes very high, and separation and collection become very difficult. So one way is to modify the water content by modifying the feedstock, by modifying the process. But when you solve one problem, you frequently create another problem.
Yeah, thank you. So there are a couple of questions more, maybe just one more then to close this question and answer session. So what would be the impact of contaminants, for instance, in post-consumer wood?
I'm sorry, again, I didn't get that.
What would be the impact of contaminants, for instance, in post-consumer wood?
Well, there's a whole range of contaminants in wood, especially from agriculture and demolition wood. In particular, there are additives like copper, chrome, arsenic. And there was an extensive study done some years ago that measured the fate of each of those copper, chrome, and arsenic in the pyrolysis system. And this depends on the form of the contaminant and where it reports to. The creosote treatment of wood, for example, in power poles in North America, when you do pyrolysis, then you distill off the creosote and the other organic contaminants. So I think it depends what you want to do with the product and where you source the wood from. But it's important to understand the what are the non-biomass components of any waste wood, and a study of how they may behave in a high temperature environment. Some will distill, some will break down.
Okay, thank you very much, Tony. So I'm sorry that we can't answer all the questions that you forwarded to us.
I think I have given my email. If anybody wants to write to me, I'll be happy to try and answer them.
Okay, great. Yeah. So is it fine for you if you include it in the material that we will forward afterwards about this webinar, so that they can get in contact with you directly?
Of course.
Okay,
yes.
Great. Okay, thanks a lot, Tony, once again. And then I would like to hand over to Dina again. Thanks a lot.
Okay. Thank you, Thies, for helping us out with the questions in the chat. And Tony, thanks a lot again for your presentation and for answering these questions. And Thies, if you have the possibility to save the chat log, then we can try to follow up with the questions which have not been answered now.
Yes, I will do so.
Perfect. So then
I'm going to say I'm interested in knowing the questions, because it will then help to improve the next presentation. So thank you.
Sure. Good. So then I would like to hand over to Gerhard Muggen for the second presentation. Gerhard is Managing Director at BTG BTL, and as such he is responsible for the overall business and the commercialization of the pyrolysis technology. He will explain their own technology, possible applications for the resulting pyrolysis oil, and the progress they have made in the industrialization of the technology. So again, I would ask everyone else to mute their microphones, and Gerhard, whenever you're ready, please, the floor is yours.
I'm ready. Just to check, can everyone see my screen at the moment?
I can.
Okay, very good. Then welcome to my presentation. In this presentation, I will shortly present to you the commercial development we have done in the last couple of years, and I also will come back to the future applications I'm seeing. Something about our company, about our technology, and about the fast pyrolysis bio-oil applications. Who we are. We are a technology provider, and we consider ourselves a product leader to commercialize the deployment of fast pyrolysis technology. Yeah, I want to make it very explicit that we are only using biomass residues, also known as the second generation. Advanced biofuels, it means that we are not competing with the food chain, which is a very important aspect of our technology. Developing a technology is costing quite a lot of time. In 1987, BTG started as a spin-off company of the University of Twente. Started with the pyrolysis technology shortly after that, and BTG have delivered the first fast pyrolysis plant to Malaysia. That was the scale of 2 tons per hour. And in the end of 2007, BTG decided to have a separate company called BTG Bioliquids to commercialize this original BTG rotating cone technology. Well, it's costing us quite a lot of time to come to the next project, but we managed to have a financial close in December of 2013 to build our own plant, Empyro. And the only intention of Empyro was to show to the world that this fast pyrolysis technology, originally developed by BTG, was a success. And it proved to be a success. We have made our first oil in March of 2015, and since then, step by step, we increased the amount of pyrolysis oil we made. In 2016, we have closed a cooperation agreement with Technip FMC. I come back to that a bit later. And at the same time, we also started our BTG Bioliquids webshop. And the advantage of this webshop is that we enable other people to create more value from the pyrolysis oil. As Tony have described, it's of course good to use pyrolysis oil for energy and heat applications, but it's also very interesting to go to high value applications. And we are encouraging people to buy the oil from our web shop. You can just go online, just use your credit card, and next week you have the pyrolysis oil in your offices. it will really smoothen the development of high value applications of pyrolysis oil. Last year we have sold Empyro to Twence. Twence is a local company here making power and heat from waste in the Netherlands. We have sold our plant, a new plant, to Green Fuel Nordic in Finland, also 5 tons per hour plant, and we have sold a plant to Pyrolysis in Sweden. I come back to that a bit later. Cooperation with Technip FMC, which is a very important enabler to roll out our technology. What Technip is doing a lump sum turnkey project, and for both projects in both Sweden and Finland was very important. There was a large player behind us to support us in especially the performance guarantees. And together with Technip, we are now delivering both projects, both for Finland and to Sweden. This is a picture of our plant Empyro. It's as I mentioned to you, and the first oil was produced in March 2015. Plant capacity, we're going in with 120 tons of dry biomass per day. It's a wood residue. Output is around 20 million liters of oil, more than 2,000 megawatt hours per year of electricity, 80,000 tons of steam, and equaling around a CO2 reduction of around 24,000 tons per year. As you can imagine, it was our first commercial plant, so it cost quite some time to get it online. The good thing was that we quite fast managed to use the first oil. But to give you an impression how long it take, in the first year we produced 1 million liters of pyrolysis oil, and now we're producing 1 million liters of pyrolysis oil every 2.5 weeks. So you can see that, yeah, developing a new technology is costing time, and you need to be patient, continue working, step up every time you're falling down. So it's really important to be prepared to go through this long route of technology development. If you look to the overall energy balance, we're going in with around totally 25 megawatt of thermal energy, converting it into around 15 megawatt of oil, around 8 megawatt of steam, and we have around 10 to 15% losses. So the total efficiency is quite high, 85%. In Empyro, we're not only making oil and heat, we're also making electricity. We have a steam turbine at site, and this steam turbine is using around 2/3 of the electricity is exported, and 1/3 is used for our own use. Well, Empyro was delivered successfully, as I mentioned to you, and very happy we can say that we have a contract for delivery of 2 new plants, one for Finland. It will be delivered in Lieksa, Finland, and one will be delivered to Sweden. It actually is a kind of copy-paste of Empyro. That was the good thing of having Empyro. Both customers have been visiting Empyro quite some times. We even have done a test of the biomass residues on Empyro. So we have tested the biomass residues of the customer at Empyro. And it was really important to show to the customer we can do it. You can say that pyrolysis oil have been quite a long time promising, but now we are proving that we can do it. What is interesting to mention is the scale of the plant. All the plants are in a scale of 5 tons per hour. And I strongly believe that you should not build these plants too large. It should be a good size. 5 tons per hour is a kind of intermediate size, 25 megawatt. In the biomass world, it's considerable. In the petrochemical world, it's small. But I believe that this conversion of the crude biomass to the crude oil should be relatively small. So I would say that we are scaling by numbers, and we're not scaling by building huge plants. The biggest reason is that transportation of biomass can be quite expensive. So we believe that you should build these plants very close to the location where the biomass residues are. A picture of the plant of Greenfield Nordic. Of course, it will be located in quite a cold surrounding. So this plant is designed to at around minus 36 degrees Celsius, so which is very important. And the rest of the values are the same as with Empyro. The project in Sweden, Source to Tank. The exciting thing here is that the crude pyrolysis oil will be directly used by Preem. They will be used in their FCC, a co-blending rate of around 1%, equaling around 15,000 family cars can be powered per year. And the good thing is that it is complying with the European Renewable Energy Directive, number 2. First startup is expected in 2021, and with the project in Finland, we expect to have the first oil this year. You may have seen our LinkedIn message. We are now doing the factory acceptance test of the Finnish plant at this moment in the Zeton premises. So the plant will be sent end of June to Finland, and then will be built at site in within a couple of within around 8 to 10 working days. Yeah, what is the advantage? Of course, it's a CO2 neutral process, high operating plant efficiency, and the interesting thing for our technology is the complete plant can be run by only one operator. And we are even now thinking about the current plant and Pyro to run unmanned in the nighttime. Exciting is the modular design. So the complete plant is built together here at Zeton. It will be dismantled, sent at site, and built up at site in around 8 days. Very exciting and very fast, and especially in those low temperature climates, it's very interesting to have this modular design. Turnkey plant at a low capex. Looking to other types of feedstocks at this moment, the silo is now finalized at Pyro to be able to handle more types of woody biomass residues. And at the same time, we also are now installing a DeNOx at Pyro to also allow other use of biomass. Yeah, why would you go to pyrolysis? Pyrolysis works with quite a variety of biomass feedstock. Greenhouse gas savings are well above other biofuels, can be used for heat, power, and transportation fuels. And actually, pyrolysis is a kind of link. It's linking the biomass world into the petrochemical world. Using biomass directly for petrochemical use is almost impossible. That's why it's very interesting to go to a liquid to make this connection between these two worlds. Very shortly, Tony already explained it very well, so I cannot add too much. We are heating biomass to around 500 degrees Celsius. You're not allowing oxygen, you're creating a kind of oily smoke, and this oily smoke is condensed in our condenser. And we're using the remaining products like the gas and the char to drive our own process. I hope you can see my pointer. What we do is we have biomass here on the inlet, we have sand circulation here, and we're doing a kind of mechanical mixing of hot sand and biomass. The oily smoke, which I described, are going here. Oily smoke is going to our condenser, and the sand and char are sent to our char combustor. And the char is burned here in this char combustor, and is reheated again to the 500 degrees Celsius. So you can see this circulation, sand and char, sand heated up again, and the sand of around 500 degrees Celsius is going back to the reactor. Of course, that's not all. You can see here the flue gas. Flue gas is going out as you separate it to the heat recovery steam generator, which is not indicated in this picture, is here. So we're making steam in the boiler, and we're making steam at our heat recovery steam generator. This is the total process. As mentioned earlier, total efficiency around 85 to almost 90%. It is very important to use the heat. Heat can be used, in our case, in Pyro to deliver to AkzoNobel, which is quite a nice income stream. And the steam in both projects in Finland and in Sweden is used to dry the biomass, which is very wet in those cases. Applications. You can see on the left side, it's an exciting picture developed by BTG. You can see on the left side all types of biomass residues. This is, for example, the empty fruit bunch. Here you can see the wood residues. And we believe it's very important to make a crude oil on one location, transport this crude oil, and then to another location, then you have two possibilities. The first possibility is to use this crude oil directly in combustion, gasification, or the co-FCC refining. And the second option is to upgrade the pyrolysis oil, fractionate, and go here to the high value applications. I will not go into detail in all these applications. That's not the intention for this presentation, but for me it's very important that more and more people will use the crude pyrolysis for these high value applications. I give this presentation quite a lot of time. On the right side, you can see low added value and high added value. I typically ask the audience, where you want to be? And people say, of course, I want to go to high value applications. At the other hand, I'm convinced you should always start here. Start here with the low added value applications, and then step by step climb the ladder, and in the end to make bio-based materials, and still the residues can be used for power and heat. And that's the mistake I see a lot of companies making. Only concentrate here on the top part, bio-based materials, forgetting the lower part, and then you can see that there's always a horizon of 5 to 10 years away and nothing will be successful. So start here, low added value, and step by step climb the ladder. Overview, which I mentioned to you earlier, I strongly believe in bringing this relatively small pyrolysis plant to the biomass, and pyrosized, decentralized pyrolysis plants, converted into a crude pyrolysis oil, and this crude pyrolysis oil is sent to a refinery. And when you're co-feeding around 5% pyrolysis oil, you'll have to around 1 to 2% advanced biofuels, which is an exciting opportunity, which is one of the cheapest opportunities, most cost-effective opportunities there is in the market at the moment. The oilet and pyro is used in our in a boiler with Friesland Campina. Friesland Campina, you can see here the crude pyrolysis oil and the natural gas is fired in a boiler. It's the co-feeding of pyrolysis oil, and Friesland Campina is reducing around 20,000 tons of CO2 per year in this application. In this picture, you can see the possibilities you have with pyrolysis oil. You can see here on the left side again the same biomass, the conversion unit, which is the pyrolysis plant, and then you have several options. The first option is to bring this fast pyrolysis bio-oil until around 5% directly to an oil refinery with no hydrotreating at all. A very cost-effective route using the existing infrastructure. Other option is to upgrade the pyrolysis oil, that's the BTG technology, with the Piccola catalyst. It will be done in 2 steps. After this first step with Piccola, you could go up to around 20 to 30% in an FCC. And if you want to go the complete chain, you can go to make the best quality. You go here, you can see MTF. You're going to transport fuel directly without using the existing infrastructure. We strongly believe in the step-by-step approach. Now you can see here co-feeding of pyrolysis oil, which is done by Preem, and step by step you go to a higher quality and higher blending rates in an FCC. Going back to the fast pyrolysis route, how does it work? Co-feeding of pyrolysis oil in an FCC, it's actually extremely simple. You are co-feeding this pyrolysis oil until a rate of 5% directly in the riser. And the funny thing is that until this 5%, you will not see a fundamental change in the properties of the FCC. So yields will typically be the same gasoline yield, the same kerosene yield, the same LPG yield, so no fundamental change. If you go higher than 5%, which is not, it's possible, but then the efficiency goes down. So until this 5%, you have an excellent efficiency. If you go above, then it's better to treat the pyrolysis oil to a higher quality, and then you can go to a higher blending rate in an FCC. Developments at the moment, co-processing. Preem is the first one worldwide for co-refining the crude pyrolysis oil. We can see more and more interest from other major oil companies who are now investing in this co-refining route, which is of course very interesting for us. The Renewable Energy Directive is interesting. Why is it interesting? Because we do not have to compete against the oil price, because there's a mandate now for co-feeding of this. There's an obligation to blend a certain percentage of second generation. So pyrolysis oil is one of them, and because of this obligation, we do not need to compete against the crude oil. We can compete against our closest sustainable alternative, which is very interesting for us. So even if the price of the crude oil goes down, actually we do not mind too much. Ratu mentioned before already, we have published a position paper assessing the suitability of the various co-processing methodologies, also highlighting that the C14 analysis is not suitable and the bookkeeping method is needed. And we are at this moment in in-depth discussions with EU policymakers on the topics which are now ongoing. I'd like to summarize as follows. Fast pyrolysis is proven at the moment, commercial scale, worldwide capacity is expanding. The current pyrolysis application is renewable heating oil, and now also in the near future the co-processing done by Preem in Sweden, and more applications of pyrolysis are under development. We consider that pyrolysis oil is a starting point of the bioliquids refinery. Thank you very much.
Thanks a lot, Gerhard. So that is really an impressive development that you've made and the company has made.
Thank you.
Of course, acknowledging that the first steps take a long time, but you seem to be on a very, very promising path right at the moment. Very exciting times for you. Again, I'm sorry, I cannot see where the questions in the chat are, so I would ask Thies to again read out questions to us. We still have about 20 minutes time entirely for this webinar, so we can afford 15 to 20 minutes of questions if there are as many questions. So Thies, can I hand over to you?
Yes, for sure. So maybe I can read a few, and then if it's fine for you, I can also unmute the participants. So if somebody wants to bring up another question, if it's fine for you, just that we have a discussion with the participants, if it's fine. Or will you? Okay, great. So one question was, well, you mentioned this feedstock of 5 tons per hour. So the question is, what is the annual capacity in liters? What is the volume of wood required in dry tons?
Yeah, it's we are producing around 20 million liters of pyrolysis oil per year, which is equaling around 24,000 tons of pyrolysis oil, and you would need around 35,000 tons of dry biomass.
Okay, thank you. Can you please give an indication of the capital expenditures and the cost of production?
Yeah, of course, it's always dangerous to give those budget figures, but there's a kind of, if you would like to have a kind of ballpark figure, the capex value of around 25 million euro is suitable. But of course, it completely depends on the local situation, civil works, connection to the biomass side. But if you would like to have around figure 25 million, if people are interested to dig into more detail there, it's fine if they send me an email, and then I can make a first feasibility for them, just to have a better understanding of how the capex and opex is working out.
Okay. Then a question regarding the feedstock. So, in case of the plant that you mentioned, it's basically wood, but is there a seasonal impact on the availability of biomass? And if so, how do you compensate for the seasonal differences?
Yeah, of course, yeah, wood is of course, as Tony also mentioned, is a nice and clean feedstock. So it's an easy one to use. BTG in the laboratories have done 50, 60, 70 types of biomass, so we're not afraid of other types of biomass. But the disadvantage mainly is that, yeah, it's seasonal indeed. If you would like to design a system, what you could do is to waste it, for example, for 2/3 of the year for an agro residue, and 1/3 you can use for wood. So if you design the system based on agro residues, you can use it for wood. It's not the other way around. So it's actually most customers are choosing for one feedstock, and they try to solve the seasonable availability. But it is possible to go for more types of feedstock, but then the efficiency goes down a bit. So it's a matter of choice for customers.
Okay, thank you. Then a question concerning the decreasing fossil fuel prices in the recent months. So how is this affecting the deployment of bio-oil investments?
Now, the good thing of the Renewable Energy Directive is the fact that it's bluntly said, but we don't mind, because it's an obligation to blend. So in 2021, 0.2% should be second generation biofuels, and in 2030, around 3.5% second generation biofuels should be blended. So even if the oil price would go to zero, they still have to do it. So I will have to compete, for example, with the second generation ethanol, of course. I feel comfortable there that we have a good solution there. And I believe there will be several solutions, second generation solutions on the market, and they all have their own market.
Okay. Then a participant wrote about a concern that the process to produce pyrolysis oil is not stable. If that's the case from your point of view, which method do you use to maintain the stability?
I can tell you that I'm now working in this field for 12 years, and the instability of pyrolysis oil has been kind of famous. It costed BTG 8, 10, 12 years to make a nice quality oil, and that's extremely important. I can tell you that if we use wood as a starting point, we are producing a stable oil, and stable means stable for 1 or 2 years. So if you want to store the pyrolysis oil for 1 or 2 years, it's okay. What is advised is that if you store it longer term, is to circulate it. Some people of you may have experience in, for example, heavy fuel oil. It's quite normal to circulate it over the tank. That's the same we do with pyrolysis oil. You don't need to heat it. You don't need to heat it. Just circulating it on the tank, and then you can easily use it for. You can easily store it for 2 years. No problem at all.
Okay, and then maybe just one last question before we open the floor to further questions. So in your energy balance, you mentioned hot condensate. Do you add it to the feedstock, or is the hot condensate used otherwise?
That question I don't understand. Should I go back? Hot condensate, 1 second. Hot condensate is, in our case at Pyro, we're using boiler feed water from AkzoNobel. That's the reason we have hot condensate. So we're starting with boiler feed water, and we're circulating it.
Okay. Yeah, thanks a lot. So if there are any more questions, so the participants send a couple of more questions during the presentation. So maybe you can give a hand sign, and then I can unmute you so that you can ask your questions directly to Gerhard or Tony. So we have Don Roberts. Please ask a question.
Yes, you had mentioned that the C14 approach is not suitable and that you're advocating a bookkeeping approach to tracing biogenic carbon. Could you elaborate on the latter bookkeeping approach, which you're suggesting?
Yeah, we have made a document which is downloadable on our website. If people are interested, I can send them directly to them. The main problem is it's not accurate. So you're doing a kind of C14 analysis, and you can see with this low co-feeding percentages, it's not accurate enough. That's the simple translation, and that's why we advise not to use it, because then you're measuring something and you don't know what you measure. But we have quite a long research document, so if you're interested, please let me know. I can send it to you.
Okay, and another question by Omar Abu Ela Zayem.
Yeah, hi. My question is for Professor Bridgwater. I just wanted to ask about the molten salt pyrolysis. You haven't mentioned it in your presentation, using carbonates or halides. So is it now not that applicable technology for fast pyrolysis? Thank you.
Just had to find my little symbol for a microphone. Can you hear me all right?
Yeah.
Hello? Oh, sorry. Molten salts have been looked at occasionally for many years, but there's currently a European project called ABC Salt that's looking both at the pyrolysis and the upgrading of the products within a molten salt environment. And if you want to know more about that, I suggest you have a look at the ABC Salt website.
Yeah, okay. Thank you. Thanks very much.
Okay, any more questions? For the moment, I can't see any other hand sign. If you would like to ask a question, please click on that hand sign. Which is not the case for a moment. Okay, thank you very much for the presenters. Dina, do you want to add something?
Yes, thank you, Thies. So I would then like to wrap up. Thank again Gerhard for his impressive presentation, and Tony for all the insight into the basics of the technology. Thanks for the questions from the audience and for being with us for around 1.5 hours. So I hope you found this one interesting, and I hope that you would probably also join us for the twin webinar, which I mentioned, which will be held on the 8th of June, which is exactly in 2 weeks, at the same time, which is 2 p.m. Central European Summer Time. As for this webinar, which we just held, we will post the presentation slides and the recording on the ETIP Bioenergy website. And Thies, I suppose that we can send everybody who has registered a notification about this, so that everybody can access this afterwards as well. We are planning further webinars of the ETIP Bioenergy Working Group 2, and we think that the topics for the upcoming webinars would probably be cellulosic ethanol and torrefied pellets. And we intend to hold one in September and the other one in November. But we will keep everyone posted on this anyway, and use our ETIP Bioenergy outreach channels to inform everybody. So with this, I would like to thank everyone again for participating, and I'll close this webinar. Thank you.